Okay, so I have the go-ahead to start. And let me say, I wasn't really planning on presenting today, but Shan shot me an email and said there was a couple of weekend slots that were open. And so I said, okay, I can put something together. And I'm just saying all this because I'm presenting a project that's very much a work in progress. In fact, I was working on the app feverishly this week to make some progress, but I'm going to present what I've been able to put together for the last couple of months. And I don't have a problem at all. If you have a comment or a question, please feel free to put it into local chat. I've got that up on my computer. I'll be monitoring that, and I'll be happy to stop at any time. In fact, my presentation is rather quite short. And I do that, one, because I only have a certain amount of material to present at this point, and two, I love having time for your comments and thoughts. So again, feel free to chime in. So the topic of my presentation today is quantification of fossil data and update on the Fossil ID app. And I presented at Science Circle before on this topic. I believe it was a year or two ago when the app was in much more primitive state than it is today. My name is Dr. William Schmachtenberg, SL name Day Miami, and there's my email address, wschmachtenberg@gmail.com. That's the one that I track every day. So if you want to get in touch with me and get involved with this project, feel free to do so. In fact, one of the things that I've been thinking a lot about is global collaboration and how we could work together more on a variety of different projects. I was just talking to Mike Shaw before the lecture started about silicon-based life. So, of course, that's the really cool part of what we're doing here is the sort of interdisciplinary approach. But I'll say more about that later. All right, so let's go to the first slide. And I know it may take a minute or two to res, and I'm going to apologize in advance. I know some of the graphics are not the best, partly because some of what I tried to photograph was low contrast, but I'm going to verbally go through everything on the slides. So here's where I started. I'm an earth science teacher in Virginia. I mostly teach high school earth science. But I also have taught and am going to teach geology and paleontology at the college level at Ferrum College. I took a year off last year so I can sympathize with Mike Shaw's sabbatical, but I'm going back this fall. And I also am involved in several research projects at this point. I'm a research associate with the Virginia Museum of Natural History. I'm also working with Virginia Tech on this app. Both of them have expressed an interest. I also work with the Department of Mines, Minerals, and Energy in Charlottesville, Virginia. I gave a lecture up in Northern Virginia a number of years ago on fossils, and I met the director, and he generously gave me a copy of Charles Butt's classic work on the geology of the Appalachian Valley. Back in 1941, this monograph was published, and it remains to today the classic work on the fossils of Virginia. It's an extremely rare publication. I was very grateful that David gave me a copy of it to work with because it's a great starting point, and it gives me a feel for where paleontology is or was back in the 1940s. So. Needless to say, I've gone through that classic reference, and you might say 1941, do people still use that? And the answer is yes. I went through all the illustrations, of course, are black and white. The classification, the taxonomy is extremely simple. As I started paging through it, I immediately started to make some mental notes. For example, he identified this fossil, this sort of oval fossil, is Lingula. There's a lot of brachiopods that are in the book. He's got thousands of them that are identified because they're the most common type of fossil that you can find. For those of you who haven't done fossil collecting, brachiopods were two-shelled. They're sort of like clams. They have a superficial resemblance to them, but biologically they're not related. They lived in the ocean, either on the bottom or in the sediment. Their ecology is actually quite interesting, as is their evolutionary history. They still exist today. In fact, this type of lingulid brachiopod can still be found in rather shallow water. So this is sort of an interesting evolutionary story that I'm going to get into as well. But basically what geologists have done, every time they find an elongate oval shell like this, they tend to call it lingula. And as there's problems associated with that. And modern scientists, modern paleontologists now recognize that the true form of lingula, this thing, basically the shell sort of looks like, if you look at your pinky fingernail, that's sort of what a lingulid brachiopod fossil looks like. And we now recognize that true lingulids are only found in pretty much modern seas, or maybe going back into the Cenozoic 65 million years ago. But other scientists, other paleontologists have tried to identify lingulas far back as 500 million years ago. Using modern references, namely the Treatise on Invertebrate Paleontology that we now have available at the museum, paleontologists now recognize that what Butts was calling lingula is probably Glyptoglacella, is the modern name that's associated with it. So part of what I'm trying to do is go through, we've got so many fossils in Virginia. There are 5,000 specimens, for example, just at the Virginia Museum that we got from Virginia Tech. And a lot of them we need to go through and update the taxonomy, update the classification, if we're going to really be able to do interesting evolutionary studies and say something about it. But back in 1941, pretty much anything went. So, for example, Butts had a really bad habit of naming fossils after himself. By the way, you might have trouble seeing this slide, so feel free to zoom in on it. This is a really nice-looking trilobite called Olenellus, and I could talk a whole hour just on Olenellus. They were some of the oldest, believed to be some of the oldest fossils that were ever found in North America. For a while, when I was going through school back in the 1960s and 70s, Olenellus was considered the definition of the beginning of the age of life, the Phanerozoic, some 540 million years old. And Olenellus specimens are commonly found in Smithsonian. I've seen them at the American Museum of Natural History. Back in the 1960s, studies were coming across proving that these trilobites, these things that sort of look like modern-day crabs and lobsters and so on, actually are not the oldest fossils that we have, not by any means. They found older trilobites clearly pushing back the age of the beginning of the age of life. In fact, we now have Vendian soft-bite organisms from Australia and so on that now indicate that advanced life began with the Vendian as far back as 600 million years ago. But what Butts did was he would find a really nice specimen and he'd say, yeah, I'm going to create a new species. I'm going to call it Olenellus buttsi, when really he didn't have any sort of scientific basis for doing that. He found one specimen in Alabama that looked really great, but it was the same age as those found in Virginia. And he really should just keep things same species name. Nowadays, it's highly frowned upon if you name a fossil after someone else, and I think that's a good idea because it really muddies the waters. And he didn't just do it with trilobites, he did it with a number of specimens that he really liked. Modern taxonomists, of course, are synonymizing all this. All right, here's another example of where we have a really classic ancient work on fossils of Virginia and just needs to be updated. Spearifer is a beautiful brachiopod fossil. I'll show you a picture of them in a minute. And just about anything that had wings and sort of spines on the side of the wings was called a spearifer. Butts identified 27 species in this classic work. We now recognize that spearifer is limited to the Carboniferous, a very short interval of geologic time, about 280 million years ago, and Butts was applying it to fossil forms that were much older than this, hundreds of millions of years older. And Worse, this genus Spirifer we now know recognize 27 species now recognize or represent probably 3 or 4 not only genera but also families of different types of fossils. And you might say, well, why is this important? Why? This is a lot of work going through, and unfortunately, there's only a couple of us left, paleontologists, that are doing any of this in Virginia. And the answer is, well, if we're going to look at evolutionary problems, we really got to clean up the data. And here's an example of what I'm talking about. When I was going for my PhD at the University of Chicago, I was fortunate to study under Dave Raup and Jack Sapkowski and Tom Schaff. These were the leaders back in the 1980s. And this is a graph from one of Jack Sapkowski's papers. And what Jack basically did was he counted up the number of species for each geologic time period, and he plotted. It's a biodiversity curve versus geologic time. So the x-axis starts with the age of life, the Phanerozoic Cambrian, 600 million years ago, and goes all the way up to today, and he's plotted the number of families on the y-axis. And Jack really has tried to go through and clean up the data as much as possible, and that's why I'm saying if we don't look at some of these classic works and resolve them, then the numbers are all going to mess up. The graph isn't going to have a whole lot of meaning to us. By the way, this comes from one of the textbooks. To give you an idea about how influential Dr. Sapkowski's work is, this was actually from an earth science textbook that I use in my classroom. Sadly, the publishers don't even acknowledge Dr. Sapkowski's work. That's why I put his name at the bottom of the graph here. All right, so let's get back to the topic, quantification of fossil data. I have a quick anecdotal story. Being a high school teacher, one of my jobs is to teach students the various types of rocks, the various types of fossils, and so on. And I do the best job I can. For example, in Virginia, students are required to know the 3 main types of rocks: igneous, sedimentary, metamorphic. And then the subtypes, intrusive, extrusive, clastic, non-clastic, foliated, and examples of each. And as we get ready for the state test, I stand up proudly at the front of the classroom and hold up a rock and say, okay, who can tell me about this rock? And one of my high school clowns will say, it's a big one. And I'm going, oh my gosh, and you're going to take the state test in a week or two. And some of the kids laugh and so on. But the sad part about that is that I see a similar sort of thing. What you have in front of here on this slide is an excerpt from a fossil. I'm not going to try and pronounce it. My Latin is not the best. It's a brachiopod found from the Treatise on Invertebrate Paleontology. And the text may be hard to read, so I'm going to read it for you. It says, shell is small, elongate, oval, and slightly unequal valved. So even the top professional publications in paleontology are quantitative, and I don't understand why that is. There are so many tools that are available, from statistics, from math. Yeah, the math's going to get a little ugly here, Penny, so you might want to close your ears. But there are so many tools that are out there that allow us to quantitatively analyze fossil shapes. And that's what I'm trying to do, is provide these tools for education, both at the high school level, college level, university level, even for researchers. And that's what my next slide is. So for a long time, I've been very interested in Fourier analysis. I've been writing an app that allows people to quickly and easily do a Fourier analysis or shape analysis of different fossils. It's on my website. I'm going to give that to you in a few minutes. The app is totally free. I'm paid. I basically do a lot of it during my planning period at the high school. So the state of Virginia essentially is funding this, which is nice. And the other thing that's really good is that I've got several high school students that are helping me beta test it. And they go through the program and tell me, yeah, this isn't working. High school kids are great if you want to see what they can break. So basically, I'm not going to go through all the math, okay, for a Fourier analysis. There are plenty of publications that are out there that have done an amazing job with that. But I do want to explain a little bit how it works. Basically, what you do is you take the shape of a fossil, and you see that here in this sort of brown box. You see the white line? That white line basically represents the head of one of these trilobites, so these crab-like organisms. And what the app does is it requires you to put in different parameters. You have to put the length, it's from the top of the bottom to the head. You put in the half width, which goes from the side to the middle of the shell. And you're clicking as you go along. So the first thing the computer does is figure out how many pixels are in a centimeter on this fossil. And it needs to do that for both the vertical and the horizontal dimensions, because there may be problems with the aspect ratio. So I wanted to fix that. Then the next thing it does is there's a built-in digitizer. So you see a series of black radial lines that are coming off the bottom central part of the shell. We call that the beak for brachiopods. And the purpose of those black lines is to allow you to line up measurements. So you just click where the black lines hit the edge of the shell, and you can very quickly and easily get about 18 different radii. I like using about a 5-degree angle as I go through. I find that gives me pretty good results. And then what it does is it takes those radii, calculates the average radius to start off with, and it fits a circle of radius that's equivalent to this average radius around the shell. Well, the problem is that most shells are not perfect circles or semicircles. So it then uses sine and cosine functions to tug at that circle until you get pretty good alignment. By the way, if you look closely on the left-hand side, you'll see a bold white line. That's where the computer connected all the points that I clicked on the shell. And then the red line that's shown there represents what the computer thinks the shell looks like based on the mathematical formulation of this Fourier analysis. So basically you end up with the average radius, and you end up with a series of numbers called harmonics, A2, A4, A6, A8, so on, that just represent the shape of the fossil. And in a minute, I'm going to give you some examples of how to interpret those numbers. Again, I don't want to get too deep into the math. Like I said, there are plenty of references out there that do a lot better job in this. All right. So I have several versions of this app. I've got one that I use at the high school level. I've got a second one that I use when I teach at Ferrum College. I've got a third level that I'm using for the university and for research level, and there may even be another one coming on the horizon after that. And if we have time, I'll explain that. But basically, here's the high school version. One of the objectives that the state of Virginia asked me to teach is how fossils can be used to determine geologic time. And for a long time, we did the traditional sort of activities where the students would look at fossils and, they'd be told how old they are already and draw a picture of them and so on. And I really thought that we weren't getting at the heart of the state objective that Virginia wanted me to, which was really to give a fossil to a student, have them identify and come up with a geologic age. And I quickly realized why the state doesn't require that. It's because it takes a lot of training, a lot of experience to get to that level. It took me years before I could, reasonably come down with an identification. Even nowadays, there are some things I look at and I'm not quite sure what they are because they're so bizarre in the past. So instead what I did was I came up with this app, and there are 8 fossils from a variety of different time periods, everything from about the Cambrian all the way up to modern day. And they run this through the program, and then there's a built-in database where I've already analyzed certain standards, certain fossils that everyone agrees, like Olin Ellis and Chesapeake and so on. So I ran them through the program and got the numbers for those fossils, the average radius and the harmonics. So they're in the database embedded in the program. And then when the student does it, they get their numbers and they do a Euclidean distance calculation in a hyperspace. So they pick, based on the unknown, they match it up with the standards. And the computer mathematically gives them the one that's the closest fix. And students, they do a pretty good job with it. By the way, the state has been amazing. They have given me rights to use Dr. Butt's monograph in my app. So when a student goes through and they analyze it, um, a picture will appear that's the closest to the one that they're unknown. The state is also giving me data on where certain fossils were found. So in the lower right-hand corner, you see a geologic map. And I think this is really important because what the app does is it allows the student to take measurements. So one, we're hitting STEM here, right? Do you notice how I'm talking about technology? I'm talking about math, and I'm talking about science with all these fossils and geology. Um, and we're doing it in a way that objectively identifies the fossil. So it eliminates a lot of biases. So when the student goes through and does the analysis, they get an identification based on their measurements, and then they compare it with field data. And there are students that come back and they say, wait a minute, this was found in rocks that were 500 million years old, Ordovician, but the fossil, the computer says the fossil should be Cambrian, 570 million years. So students are starting to say, well, either I made a mistake in the analysis, and sometimes they click on the wrong things, and I tell them, go do it again. Or what it means is that the identification is incorrect, all right? The data is usually pretty good. And so they'll start playing around with this in their head. And, maybe it's a matter of they've got to redo the analysis. So I think this is a lot better than the way paleontology was done. Paleontology has just been so descriptive and qualitative that we really need to move the whole science into the 21st century. And that's what this app is all about. All right, so results. Here's some data for us to bite our teeth into. The high school students are doing amazing. There are 8 K-12 fossils in there. And some of my students do such a great job. They actually go and they analyze some of the college versions. On average, students can identify 10 out of the 13 fossils within an hour. I think the last time I did it, they were successful within 45 minutes and an accuracy about 80%. I think that's pretty good for high school kids, getting it down to the species level and coming up with an age. The last time I offered the fossils class at Ferrum College, I had a number of students that just struggled with the material. They had a real hard time. They were interested in fossils, but they had trouble with the morphologic features and the taxonomy. And I remember I gave them a traditional index fossil lab, and the results were abysmal. I mean, the average was 17%. It's the worst I've ever seen it. My best students were bragging about getting 40% on that lab. And I'm going, well, what do I do? Because if I include those scores, most of them are going to fail the class. So I said, next week I went in, I reviewed as a good teacher, went over as much of it I could, and then I said, you're going to use the app. And the results were absolutely amazing. The average went up to 90%. Students were doing a great job. I think they're part of the digital generation. So with some practice, they got used to how to use the app, and their identifications were increasing. Yeah, I was absolutely shocked by that result. The majority of the students passed that class because of the app. All right. So here's a little bit of how we can use this program for research purposes. So one of the things that the state and Virginia Tech and the museum is interested in is including more fossils in it. All right, so far, when I first created the app a couple of years ago, I picked 8 representative fossils for high school level and a few more for college. But there are thousands of fossils. So one of the things that I did was I went through the orders. There's about 20 of them with some of my high school students. And I just picked representative forms of the major brachiopods, the major fossils, and ran a Fourier analysis on them and got some very interesting results. And again, I'm sorry for the quality of the slide here. But basically what I found was if you look at the bottom of the slide here, you can see these sort of lingulate brachiopods that sort of look like your fingernail, your pinky of your fingernail. They're sort of elongate and oval. And they fall with the lowest, the most negative A2 values. All right, then at the top of the slide, if you can zoom in on that, what you notice is the spiriferids, they have sort of wings and they're spread out. They're very elongate horizontally. They have the highest A2 values. So basically what this A2 number is, it's describing the basic shape of the fossil. Um, in terms of whether it's elongate horizontally or it's stretched out vertically. And then if you've got things that are basically circular or oval, they fall with the A2 very near zero. And basically that makes sense. If you think back to what I just said, the Fourier analysis starts with putting a circle around the fossil. So if the circle accurately describes the fossil, the Fourier analysis is great. We don't need to sort of bulge it or manipulate it with these cosine functions. So they just let those coefficients go to zero. So a couple of things popped out from this analysis. First of all, there are a lot of brachiopods, okay, that are small and circular. There's just a ton of them. So they're all clustering sort of towards the left-hand side, towards the middle, which is a concern for me because that means the Fourier analysis is not going to be able to really distinguish them very well, the circular or semicircular ones. Things that are oval, like the lingulids, the tetrabrachylids, the pentamerids, oh yeah, it pulls them apart very effectively. Or really big spiriferids, like you see on the right-hand side, it can distinguish, or these things that have wings on them that with spines on the side. It does a pretty accurate job of that. And the other thing that I noticed, so what I'm really doing is by using the Fourier analysis, I'm really creating what's called a morphospace. I'm seeing where brachiopods were able to develop, okay, in terms of their shape. And I think there's some very important ecologic lessons here. There's some evolutionary lessons. For example, if you look, I didn't put the geologic time periods that they lived on here, but basically on the left-hand side, on the left-hand side towards the middle, those are Cambrian. Those are the oldest brachiopods, about 540 million years ago. And then as you go towards the right-hand side of the slide, you go towards progressively younger brachiopods. And some of you may recall Cope's law. Edward Drinker Cope, back in the 1800s, came up with this principle that through geologic time, organisms tend to get larger. He was mostly interested in vertebrates and mammals, but it applies here towards, towards these brachiopods. They certainly were getting larger through time. We can even ask, why were they getting larger? And I think it's not just a change in terms of, say, the average radius of the slide or not. I think it's a matter of surface area. I think as we go from about 570 million years ago to about 280 million years ago, you got to look at the sediment in the rock that's there. And no doubt about it, organisms were going through, they were biotebrating, they were mixing up the sediment. So organisms and brachiopods had to worry about sinking into the sediment. And if you sink into the sediment, that's a dangerous thing for an invertebrate. If they're right on the bottom of the seafloor, they open up their shells and they can take in water, they can get oxygen, they can get food. They're mostly filter feeders, no problem. You sink a centimeter, my biologists tell me, you go a centimeter into the sediment, all of a sudden you get mud into your shell. It clogs up your feeding organs like gills and lophophores and so on. And the thing is going to die. And so the moral of the story is simple, okay, from an evolutionary point of view, don't sink into the sediment. So what I'm seeing here, and Charlie Thayer, he documented this in the 1980s, is that organisms adopt sort of a snowshoe effect. They try and spread the mass of their body out over an area that is as large as possible. So that's why the shells get larger, why they tend to get flatter. It's a very effective mechanism. And then what really interested me as well, cemented brachiopods tend to be on the left-hand side. Free-lying brachiopods are on the right-hand side. Infaunal brachiopods, like this lingulid stuff, they're on the bottom. So this graph is not only pulling out evolutionary relationships, it's also pulling out ecologic relationships, which is really not a big surprise, right? Okay, because a number of scientists, a lot of paleontologists and biologists have said that the shape of the shell should be functional. Okay, if not, natural selection is going to eliminate you very quickly from the environment. So that's what I'm seeing here. Also, I hope to use this in terms of classification and taxonomy. And I know some of my colleagues would say, is it really a good idea to use just size and shape to distinguish species? And the answer is, we do it all the time, okay? If I talk to a paleontologist, that think of a lingulid, think of a pentamerid, or a strophomenid, we sort of have an image. Lingulids tend to be really smaller, and strophomenids tend to be rounder. And taglines say bigger footprint gives bigger areas, so buoyant weight over divided by area equals pressure to the base. Absolutely. Absolutely, they're trying to do that, okay, in these brachiopods. In fact, if you look at invertebrates through time and reach some of Charlie Thayer's work from the 80s, really classic work on functional morphology of invertebrates and brachiopods, so he says it's not just the snowshoe effect. The other thing that you can do is you can get more of a bowl shape. It's called the iceberg strategy. So what happens is some organisms develop an extremely convex shell to them. Inoceramid clams that I worked with are probably the best examples in the Cretaceous with dinosaurs. They developed these really convex lower shells, so they didn't care if that part of the shell sunk in the sediment, as long as the top part of the shell stayed above the sediment-water interface. So there's a number of different ways that organisms have had to get around this problem of sinking into the sediment. All right, so the next thing that I looked at was the whole ecologic and evolutionary issue of infaunalization of brachiopods and clams. And again, the Fourier analysis does a really nice job of this. And again, the slide is a little bit out of focus, so I'll tell you what's going on. The x-axis represents the size of the shell. That's the average radius. The y-axis is the A2, okay, which represents the shape. So again, if you have a really vertically elongated shell, it's going to be a strongly negative A2 value. If it's a circular shell, you're going to be close to 0. So there's a group of brachiopods, again, known as the lingulids. They appear about 540 million years ago, and this is the time period when the oceans are just, they're the times when organisms are experimenting like crazy. They're trying different things, and you see a whole bizarre range of creatures. If you look in the Burgess Shale of the Cambrian up in British Columbia, or some of the Australian, the Vendian faunas, there's some really bizarre animals like hallucigenia that even modern biologists, they don't have any clue as to what's going on. Oh, we have a question about the math. So a Fourier transform linearizes the data points. Well, let's be careful here, tagline. There's Fourier analyses that are designed for XY coordinates. I use Fourier analysis on polar coordinate data because it just makes more sense of my for the animals that I'm dealing with here. I think you're thinking of a different sort of a math here. Actually, it's interesting. If you're into that, there's a guy at the museum that wants to talk to you. He's got a lot of XY data he wants to do Fourier transforms on. But we can talk about that later. Yeah, the term Fourier has been used in a variety of different contexts. I use it for analyzing shape, but you can also use it for analyzing periodicity in data points. There's a number of different uses for it. So anyway, to get back to the point that I was doing, the earliest of these so-called lingulid brachiopods, they start off as just circular. Some of them developed a pedicle, which is sort of a fleshy tongue. In fact, the word lingula from Latin means tongue. And it was a clever adaptation they came up with. It's basically a tongue that was used to sink into the sediment. And that's a major evolutionary advancement back about 500 million years ago, because now they've got a way of stabilizing the shell so they don't get swept away. And in the oceans, that's huge. If your shell gets swept away by the currents, you're bashed against rocks and break the shell open, and other predators can come and eat you. So the development of this pedicle was a major improvement. So that they got the pedicle, and then what happens is, as you go through time, And what you're seeing here, you see the diagonal line of these shells as you start from the upper left to the bottom right. Do you see the trend as you go through geologic time? And the oldest ones are in the upper left, youngest are in the lower right. As you go through time, do you see how the shells become more and more elongate? That's not random. Okay, there was a reason for why these organisms started to do it. And I'm not saying the brachiopods are intelligent and they designed this. No, I mean, this is talking about Darwinian evolution, variation, natural selection. So basically what happened is the ones that became elongate developed a shape that allowed them to burrow into the sediment very quickly and effectively. Stephen Stanley, in his PhD dissertation, did a great job on this. And he went through he didn't do so much brachiopods, but he went through modern clams. And what he found out was that if you have an elongate shape like the one that's in the lower left-hand corner, lower right, where you become like a knife blade, that's extremely effective for getting into the sediment fast. So what does that do? One, it protects you from the waves and currents in the ocean environment. Second thing, what it does is it allows you to hide from all the nasty predators that start appearing in the oceans. And Garrett Vermeer has done an amazing job with this. Basically, he's an ecologist, and he's sort of a paleontologist, but also a modern day ecologist. And what he found was, as you go through time, the aggressiveness of predators dramatically increased. So animals that had no trouble living in the past would be smashed to pieces if they were to exist in today's modern day oceans. You look at stomatopods with their little claws that they can fire out like bullwhips and just shatter shells. So nowadays, there aren't many organisms that want to live on the bottom of the seafloor. Most of them burrow into the sediment. They hide from these things. So infaunalization confers a major advantage upon an organism. And as we go through time with the brachiopods, we find early lingulids, they hit on the success story really early on. And so they persist. That order persists all the way up to modern day. And they improve on it by becoming more elongate. And then the clams come in, and they pick up where the brachiopods left off about 228 million years ago. And their shells are even further optimized for living in the sediment. They become longer, they become larger. These things are called, these sort of razor clams are extremely effective at digging into the sediment. And that's why clams have taken over today, and the brachiopods, we've got a couple of species left. Basically, they dominated the rocks from about 600 to 228 million years ago. Then the continents slammed together, Pangea forms, the continental shelves drain. Also, there was a glacier going on that didn't help back then. So the continental shelves drain, wipes out most of the brachiopod clades that were around. And then when Pangea splits apart, the clams take over with this infaunalization strategy. And that's why they're so abundant today. And the clams not only pick up on the pedicle that brachiopods have, they developed a very efficient foot, and they even modified their shape. So some of them can slice into, if you look at the modern venerid clams, the cherrystone clams, which I love having them for an appetizer, those things, their shells are designed to slice into the sediment very quickly. So they've dramatically improved the infaunalization component that the brachiopods started with. All right, so that's sort of the evolution story and the taxonomy I'm going to get to next. Oh, this is just another slide of that. Skip that, as I've already said. I have to there. All right, so like I said, there's at least 3 versions of the app. And there's the website for those of you that want to play around with it, www.evwllc.co. It's totally free. Everybody can use it, have fun with it. The K12 version is there. By the way, when you go to that website, there's a click on the free fossil app link, and it'll take you right to the selection, so you can pick your level for like high school. You click there. It gives sample data, or it gives a description of how to use the app. The college level is a little more difficult. What you have to do, the students have to understand the basic types of fossils, like how is a brachiopod different from a trilobite, different from a clam, and so on. And then the university version is the most advanced, and that's the one I've been working on most recently. It's got morphologic measurements. That's what Virginia Tech and James Madison University requested. So let's take a look at that version. Basically, what the other paleontologists in my state have said is they're very interested in the app at the Virginia Museum of Natural History universities. But what they've said is you really need to integrate traditional morphology or characteristics of the shell into the program. So that's what I've been working on for the past couple of months. I went through the treatise on invertebrate paleontology and I've started to put them in. And they act as filters on the database, which allows me to put a lot more fossils into the app. So instead of 8 or 13, right now I'm up to 19, which isn't a whole lot because it does take some time getting the, analyzing the standards and putting them in. I'm hoping to work with my students on that. And I hit sort of a tangent I've been working on the last couple of weeks, but that's the ultimate goal, is to include more and more fossils in this. So far I've hit on the main ones, the most common fossils in Virginia and the Appalachians, but I want to add to it and then use these morphologic filters to refine your search and make it more accurate. And so far I've been getting some pretty good results. One thing I want to mention too, if you're not a paleontologist, if you go on the website, you want to play with this, I put together a guide to the morphologic features and characteristics of the common brachiopods. So even if you know nothing about brachiopods or fossils, just want to play with this, there's plenty of guides that you can download and print out to help you or your students out, or anybody that wants, even amateur fossil collectors could try this out. My students asked for that, and I said, fine, I'll put it together. All right, so how effective is it? One of the things that I've been doing is I've got access as a research associate to 5,000 specimens at the Virginia Museum of Natural History. So I've been going through, and I use the treatise as the standards, and I think that's probably a safe bet because that's probably the cleanest database we have of modern fossil taxonomy. And then I use the fossils and the collections at the museum as sort of my unknowns. And I'm having my high school students go through it. It turns out that when I analyze the fossils from the museum, about 33% of them can be identified just on the basis of the Fourier analysis. Size and shape alone are able to give me accurate identifications. 39%, if I add in morphologic features, so I integrate traditional paleontology into the app, I get another 39% of accuracy. And if I add geologic data, like how old the fossil was or how old the rocks were that the fossil was found in, I pick up another 28%. So basically, using these database filters, geology and the morphology, I get 100% of the unknowns, which is pretty cool. So the app is pretty effective, again, if you sort of compromise and integrate it with traditional work. So where are we going from here? I'm glad you asked. One of the reasons why I'm on the science circle is collaboration, and I want to work with other scientists. So when I was at Virginia Tech the last time, one of the graduate students brought up, this is a huge project. There are thousands of fossils in there. To get them into the database, to get them so that other students could use that is going to require crowdsourcing. So that's what I've been working on. The software I use was created by, the main program I use is called NS Basic, it's App Studio by NS Basic. And I'm fortunate, the CEO of that company, George Henney, has been giving me a lot of help with this project. And he suggested moving the database from inside the app to a Google spreadsheet. And I really like that idea because this way, if you're a paleontologist, if you want to put your favorite brachiopods or whatnot into the app, you just go into the Google database. I just give you the link, and I give you rights to write to it. And then anytime anybody that uses the app, it will automatically update. The software is on the internet. The database will be on the internet. It's going to be freely accessible to anybody. I'm working with a paleontologist in Sweden next week. Let's get her into it, and at the universities. So this way I hope we can improve the speed of getting the data in. And there's a couple of concerns I have about this, but I really see that as sort of a great crowdsourcing solution. The U.S. Geological Survey, the Virginia Geological Survey would like me to add other organisms beside brachiopods, maybe snails or clams. I've been running into some technical problems with the clams. They have a much more complicated shape, so the math gets a lot more complicated. With snails, there's a whole different approach, but basically I think could be done with the database. So that is my presentation for today, and this is actually went longer than I thought it would, about 46 minutes. So if you have any questions, feel free to put them in local chat, and I am going to click back to the beginning if I can. Thank you all for coming. All right, I think there I am. I'm back at the beginning. Okay, and there's my email again, wschmachtenberg@gmail.com. Feel free to email me. I check that every day to see what's going on. Any questions about what I present? I thank you all for coming. Okay, Arian, I have a question here about how do you get the standard estimation of ages? Um, yeah, well, right. Most geologists use radiometric dating that's been going on for over 100 years now, where basically what you do is you can age date igneous rocks and metamorphic rocks that are interbedded with sedimentary ones, and you slowly build up a geologic timescale. The other thing that I've done is use estimates of sedimentary rate calculations. That was done 100 years ago, and they got a pretty accurate estimate. I got some of you wanting to go on a fossil collecting trip. Awesome. Doc, is a question: do you think it is wrong to burn coal given this full of fossils? Oh my gosh. That's sort of tangential to the question. Yeah, I think that first of all, I live in Virginia, which is a huge and traditionally a coal burning state, and I can tell you that a lot of the counties that are in the western part of our state are really going away from burning coal, and we're trying to get more and more into the renewables. And I think that's the right way to go. Virginia is interested in um, putting wind or turbines on some of the barrier islands and taking advantage of the winds. I think that harnessing and putting turbines at the base of the oceans on the continental shelf to harness wave and current energy is a great way to do it. I think solar is a great opportunity for the future as well. Okay. Yeah. Yeah. Fuman, that other website that you list, I've got two websites. Um, and I use the evwllc.co more. All right. Does anybody else have any other questions? All right. Thank you all for coming. I appreciate your feedback.